All right, hello everyone. Welcome to lesson 28 of Calculus 1. So what we're going to be doing starting with today's lesson and for the rest of the class, we're going to be focusing on how to find the area underneath the curve of a graph. So for example, let's say we have a function whose graph looks something like this maybe, and we have these two x values, a and b. One common problem we may want to solve, and it shows up in a surprising number of applications, is what is the area between this curve and the x-axis? Or sometimes we may even want to know what this area is, for example, so even underneath the x-axis. So how are we supposed to do that for a general function f of x? Well, for particular functions f of x, we can already do this using geometry. So for example, let's say our function is 2x plus 1, and we want to find the area under the graph from 0 to 2. So to draw a picture of this, we would have 2x plus 1, whose graph looks something like this, and our goal is to find this area right here. All right, well, how will we do that? Well, it turns out that the area here is going to be nothing other than a triangle on top of a rectangle. So we have this rectangle here, which has a width of 2, and then a height of 1, which is the y-intercept. Then we have this triangle, also with a base of 2, and then a height of 4. Here. So the area will be 2 times 1 for the rectangle, and then 1/2 times 2 times 4 for the triangle up here. And then we end up getting with this, let's see, we end up getting 6. So for some functions, we could already do this and we don't even need calculus for it. It's just going to be using geometry. However, these functions are few and far between. Most of the functions that we come across, we can't use simple geometry to get the area under the curve. So for example, if I make a small tweak to the function we just used in this problem, make it 2x squared plus 1 instead of just 2x plus 1, then we end up with something more difficult. So let's say we want to find the area under this curve from 0 to 3. All right, 2x squared plus 1 will look something like this on the interval 0 to 3. So we're interested in finding this area right here. Now this area doesn't have a nice formula for it, unlike a rectangle and a triangle. So at first it seems like we're out of luck here. But what we're going to do before we get the exact area of this is we're actually going to approximate the area under the curve. So we're not going to get an exact answer right away. We're going to get an approximate answer. How are we going to do this? Well, what we're going to do is we're going to draw rectangles. And for starters, why don't we do n equals 3 of them? So what we're going to do is we're going to divide up our interval into 3 equal pieces. So that means that the width of all of these rectangles will be 3 minus 0 over 3, or the final point minus the initial point divided by how many we have. And in this problem, that means that the width of these rectangles will be 1. All right, so that's the width of all of these rectangles. Then for their height, what we're going to do is, for example, the rectangle in between 0 and 1, what we're going to do is we're going to go up to, we're going to plug 0 into our function, and then that will be the height of our rectangle. So there's our first rectangle. For the one in between 1 and 2, I'm going to go to f of 1, which is a little bit higher, and then shade that in. And then for 2 and 3, I'm going to go up to where f of 2 is and make a rectangle that way. So what we could do is we could add together the area of these 3 rectangles, and they should be relatively similar to that of the area under the curve. Now, as you can see here, we're missing some area under the curve. It looks like we're underestimating here But hopefully this should end up being pretty close. Okay, so our area is approximately equal to f of 0 times 1, that's the first rectangle, f of 1 times 1, and then f of 2 times 1. All right, so this will be 1 plus 3, if I plug 1 into here, and then plus 9. So our approximation for the area under this curve is 13, but in all likelihood, it's going to be a bit bigger than that because as we can see from this picture, we're underestimating. Now, what this is called a left Riemann sum. Because for each of the interval where we have a rectangle, we're using the left-hand endpoint to give us the height of our rectangle. Now, we could do this in a different way. We could get a different approximation for the same thing. And as you might guess, we could break it up into the same number of intervals. Draw the picture again. We could break it into the same number of intervals, but instead of using the left endpoint, we can use the right endpoint. So there's our first rectangle. There is our second rectangle. And then our third rectangle will be like this. So this will be our right Riemann sum. So the area here, well, the width of all the rectangles is the same. So all of them will be 1 for the width, but the height will be different. For our first rectangle, we use f of 1. For our second, we use f of 2. And then for our third, we use f of 3. So remember, we're using the right-hand endpoints. This is called a right Riemann sum. Now, the nice thing about, if anyone ever asks you to do both a left and a right Riemann sum, the good news is that they're almost exactly the same, except the left Riemann sum will have an extra number in the beginning, and then the right Riemann sum will have an extra term in the end. We already computed what f of 1 is, it's 3. We already computed what f of 2 is, it's 9, so we don't need to do those again. The only new thing we need to do is figure out what f of 3 is. And if I plug 3 into here, 3 squared is 9, times 2 is 18, plus 1 more is 19. So our approximation for the area using right Riemann sums will be 31. As you could probably tell from the picture, this is definitely going to be an overestimate. So in all likelihood, the real answer is going to be somewhere between 13 and 30. Now, I want to talk about one more alternative to this. It's called the midpoint rule. So rather than using the left or the right, left would be an underestimate, the right would be overestimate, why don't we just split the difference and use the middle? So for this one, I have the same picture again. 1, 2, 3. This time we're going to pick the middle value to be the height of our rectangle. And the nice thing about that is that a little bit of it is an overestimate and then some of it is an underestimate. And we hope that those kind of cancel each other out. So for the midpoint, we have f of 1/2, which is halfway between 0 and 1. And then we have f of 3/2, halfway in between 1 and 2. And then f of 5/2, which is halfway between 2 and 3. So here we're going to end up with 3/2. Here we're going to end up with 11/2 if we do the arithmetic. And then here we will end up with 27. So if we add all of these together, we end up getting 41/2 or 20.5 as our estimate. All right. And it turns out that this will actually be pretty close to the true value. Oftentimes the midpoint one is more accurate, although the numbers may be more difficult to plug in certain instances. Okay, now, how can we make this approximation better? Well, one way we can make the approximation better is to use more rectangles. So for example, let's say we bumped up the number of rectangles to 6. So we double them. I'm just going to do this with the left-hand Riemann sum to save time here. I think you'll get it for the other ones. Okay, so we have something like this. But now our rectangles are going to have a width of 1/2. And we'll still use the left-hand endpoints. So our approximation will end up looking something like this here. And as you can see, this is still an underestimate. We still have these areas right here that we didn't account for, but by having more rectangles, this is going to be a bit more accurate than it was previously. So the width of all of our rectangles is 1/2, so I'll simply factor that out. And then we have f of 0 plus f of 1/2 plus f of 1 plus f of 3/2 plus f of 2 plus f of 5/2. So this is the left-hand Riemann sum using 6 rectangles. So this is going to be the width for all the rectangles, and then these will be the different heights of each one. And if we do the arithmetic here once again, and we see what we get, we end up with 67 over 4, or 16.75. Now, this is going to be a bit bigger than our previous left-hand sum, and this makes sense because we're getting more of this area that we didn't get previously, so it's going to go up a little bit. And in the same way, if we did a right Riemann sum with 6 rectangles, it would end up going down, so it would be something less than 31. So what happens in the long run is that these Riemann sums will end up meeting in the middle. So the true area under the curve is going to be somewhere in between the left and right-hand Riemann sums as n goes to infinity here. That's what it's going to end up being. And it turns out that the true answer, A, the area under the curve here, will be exactly equal to 21. So that also indicates that the midpoint will end up being a really good approximation for this, even with only 3 rectangles. So midpoint rule can be very good. All right, now how did I get 21? So where did this number come from? I didn't mention any geometry or anything like that. How do I know that this area is going to be 21? Well, it turns out that the more rectangles we have, the more accurate we get. Now, we could make it even more accurate by having 10 rectangles, 100 rectangles, 1,000 rectangles, and our error keeps decreasing every time we increase the number of rectangles. So then that sort of begs the question, what happens as the number of rectangles tends towards infinity? So we have all these really thin but numerous rectangles. Well, it turns out that as n goes to infinity, our Riemann sum will go to the area under the curve. All right, so I want to find a way, I want to write this down mathematically, but in order to do that, I want to introduce some notation. So for our rectangles, let's talk about the width of them, or a general function f of x. So now we're not just talking about 2x squared plus 1, we're talking about a general function f of x. And that's going to be over the interval a to b. We want to find the area under the curve for that region. Now what we're going to do is we're going to break this into n rectangles, and each one with equal width. So if we want them all to have equal width, we take the length of this interval and divide it by n. So it's going to be b minus a divided by n. That's going to be the width of each rectangle. And I'm going to call this delta x, because it's a small little change in x for the width. All right, so there's the width. Now, how do I know which number in general I'm supposed to plug into my function? Well, that depends on if we do a right-hand or left-hand sum here. So what I'm going to do is I'm going to give a the name x0, and I'm going to call x sub n, that will be b. So this is my initial x value and my final x value. So a formula for the x's I'm going to plug into my function, called x sub I, would be a plus I times delta x. Right, so these are going to be all of the x values I'm going to plug into my function. And if you take a look at this, let's say I equals 0, for example. Then I would have 0 times delta x, which would just give me a. On the other hand, if I go to the very last x value, n, I would do n times delta x, which would give me b minus a plus a. That would turn into b. So the nth one will be b, and the 0th one will be a. And then for all of the other ones in between, like let's say I want to go to the third rectangle, I would plug in I equals 3. All right, so that's how I get the x values I'm going to plug in to my function here. Now, how do I write these left and right-hand sums? So R sub n, so this is a right-hand Riemann sum with n rectangles. This is going to be f of x1 delta x plus f of x2 delta x, and so on and so forth. And then we get to f of xn delta x. And notice that x1 isn't the first point in our interval. So x1 is not equal to a. X1 is the first increment after a. So kind of like how in the previous examples, we didn't plug in 0 for our left or for our right Riemann sum. We plugged in the number after 0, one width after 0, which is 1. And then we did end up on our final value here for a right-hander. So we will actually get b here for the last one. And the left-hand one is similar, only everything shift backwards by 1 step. So I'm going to start at x0, which is a. So notice how in the previous example, I started at 0, which was my a for the 2x squared plus 1. And then I have f of x1 delta x, and so on and so forth. And then I get to f of xn minus 1. So I don't go quite as far as the right-hand sum does. I go 1 before that here. And we could also assemble a similar formula for the midpoint. I'm going to focus on the left and right here. Now, rather than writing all of this out every single time, one way to express sums of a bunch of quantities in a compact way is something called sigma notation. What is sigma notation? Well, it's just an alternative way of writing what I just wrote down here. So Rn, the way we would write this is we would draw the capital Greek letter sigma. We would write down what index we're using, which is I here. We write down the starting number for our index, which is 1, and then we put the ending number for I up here, which is n. And then we write down what the term looks like for every single one of these i's. So it seems like no matter what number I'm plugging in to this function here, it's always going to be f of x sub I, where I is that number, times delta x. That's what all of the terms look like. So this is what all the terms look like, and this is telling you which ones to add over. So in the same way, the left-hand Riemann sums would be written just a little bit differently. The terms look the same as the right-hand ones. They're still f of x times delta x. So that part would be the same. The only thing that would be different would be the starting and ending values here. So this would start at 0 and go only to n minus. So anyways, this is sigma notation, and this is a compact way of writing our left and right-hand sums. Anyways, if we want to get the true area of the curve, we need to make our n larger and larger, right? So it stands to reason that the exact area under the curve, no squiggly equal this time, will be the limit as n goes to infinity of our right-hand sum, and we could also use the left-hand sum as well, or the midpoint one, if we have it. So all we need to do is look at the limit as n goes to infinity of what's happening in here, and we go towards infinitely many rectangles, and that will give us what we want. So to write it a different way, we could substitute the sigma notation in for Rn. I equals 1 to n, f of xi delta x. So these rectangles will get thinner and thinner, but we're going to have more and more of them. So we're going to get things more and more active. Okay, so let's return to our example that we had earlier. So let's apply this to our particular example. So f of x is 2x squared plus 1. And we want to know the area under the curve for 0 to 3, right? So let's go ahead and compute this area here. So our area will be the limit as n goes to infinity. And I'll go ahead and use the right-hand sums, though we could easily do this with the left-hand sums as well. So this is going to be the limit as n goes to infinity of I equals 1 to n of f of xi delta x. All right, now let's substitute in our specific example in for this. So we have our limit. We still have our sigma notation. F of xi, that's going to be 2xi squared plus 1. And then what's delta x? Well, earlier we had a formula for delta x. It's b minus a over n. Now, n is a variable here. N is heading to infinity, but b and a are particular numbers. So delta x will be 3 minus 0 over n, aka 3 over n. All right, so that's going to be our width. Now these xi, remember, we also have a formula for that. Xi will be a plus I delta x. So for this problem, xi will be 0, because that's our a, plus I, and then our delta x was 3 over n. So we end up with 3I over n as xi. That means we could substitute that into here. So we have the limit as n goes to infinity of the sum from I equals 1 to n of 2, and then we have xi squared, so 3I over n squared plus 1, and then we have this 3 over n out here. Okay, so now we just need to see what's going to happen with this. Now, there's some rules of algebra with sigma notation, and I'm not going to prove them or anything. I'm just going to kind of gloss over them. So sigma notation is adding a bunch of things, right? And if you're adding a bunch of things that have a factor in common, you could factor that out. So the way that works with sigma notation is anything without an I in it that's multiplied by our expression can move out to the front. So this is the limit as n goes to infinity of 3 over n. And then we have I equals 1 to n of 2 times, and then I'm just going to square this out. So I have 9I squared over n squared plus 1. Okay, so that's what we get when we move the 3 over n out there. All right, now another thing we could do is sigma notation splits up over addition. So I can write this as the limit as n goes to infinity of 3 over n, and then I have the sum from I equals 1 to n of this part, so this will be 18I squared over n squared, plus the sum from I equals 1 to n of just 1. So I could split the sigma over addition here. All right, that's all well and good. So now let's think about what this is right here. So remember, the way sigma notation works is you plug in the I into this formula, and then you add that to your running total, and then you move on to the next I. But if anything ever has no I's in it or no place to stick the formula, what's going to happen is that it's just going to be what's on the inside times how many I's we're going over. So we can imagine this as 1 plus 1 plus 1 plus 1 plus 1, on and on and on forever, plus 1. Well, not on forever. We do it n times. We do it for every number from 1 to n. So we're adding together n ones. So that means that this is going to end up equaling n. So we have the limit as n goes to infinity of 3 over n. And then I'm also going to move the 18 over n squared out of here. And we have the sum from I equals 1 to n of I squared. And then this, we said earlier, was an n. All right. There we go. All right. Now we just need to know what the sum from I equals 1 to n of I squared is. So what is that equal to? Well, let's think about that over here. If I plug in I equals 1, that will be 1 squared. And then I move on to the next I, 2, that'll be 2 squared. And I move on to I equals 3, that'll be 3 squared. And I keep doing this until I get up to whatever number n this is. What this is this is the sum of the first n squares here. Now, this actually has a nice formula for it. I'm not going to prove it or show where it comes from, but this is actually equal to n times n plus 1 times 2n plus 1 over 6. So that's the formula for the first n squares added together. And if you don't believe me, you could plug in a small number for n, like say 3 or 4 or something, and verify for yourself that that's how it works. So what we're going to do is we're going to replace the sum of the squares here with this formula. So we have 3 over n, 18 over n squared, and then we have n times n plus 1 times 2n plus 1 divided by 6. So that's what the sum of I squared turned into. Then we have an n out here. All right, and now we're almost done here. What we're going to do is I'm going to multiply back this n through here. So this is the limit as n goes to infinity. If I do 3 over n times this stuff right here, I end up with 54 over 6. And then I have n times n plus 1 times 2n plus 1. All of that's over n cubed. So I pretty much just multiplied all of this together. And then 3 over n times n, the n's canceled, and I just end up with 3. Okay, now we got rid of all the i's and all the sigmas. Now we're just back to doing a normal limit here. Now, if we were to FOIL all of this out, this would be a cubic polynomial. This is also cubic. And the leading coefficient, if I were to FOIL all this together, would be 2. So if I look at the limit as n goes to infinity, it'll be 2 times 54, which is 108, divided by 6. Those would be the leading coefficients. So we would have 108 over 6, which is actually 18. And then we have this 3 over here. And then we end up getting that 21 that I promised earlier. This is going to be the true area once we have infinitely many of these rectangles, or as n goes off to infinity. Now, I want to quickly add, so this is a rather complicated process using something we're not quite familiar with, sigma notation. So you might be worried, okay, do I have to do this every time I want the area under a curve? And thankfully, the answer is no. What we're going to learn in our future lessons here is we're going to learn a better way of evaluating the area under a curve. And thankfully, we won't have to use all of this sigma notation all the time. So that's something to look forward to here in a future lesson. All right, that's it for today. So I will see you all in the next class.